Hey, welcome to another video on linear algebra. So this is going to be a super fun video because you deal with inverses a lot in the class, and this is just it's a great video to watch. So let's go ahead and get started. So we're going to be dealing with the properties of matrices and how to deal with their inverses. So let's look at this Gaussian elimination from row echelon form. So we have this system of equations, these two equations, and we put into an augmented matrix, and we do some row operations, and then we get this, right? So we could either do this number one, or if we go down to number two, we have these two of the basically the same equations, right? But what we're going to do is we're going to group certain stuff together. So let's just say we're going to group all these coefficients, these leading coefficients, into one matrice. So we're going to call that matrice A, and A consists of A, B, C, and D. And we're going to take all the variables, and we're going to name that X. That X is a matrix which consists of X sub 1 and X sub 2. And our constants, we are going to put that in a matrix. We're going to name it B. B is just some constant, and that's how we grouped it together. And then once we have the matrix A, X, and B, what we could do is we can say AX is equal to B, and we could also say, and this is kind of important because this is a technique that you use when you're doing proofs. Alright, so if you multiply this A inverse matrix to both sides, and there's a reason why it's on the left of both terms, but that will be introduced when you talk about the proofs. So right now, you just have to believe me. The inverse matrix A multiplied by the matrix of A, that's going to equal this I, which is called the identity matrix. So that gives me an I. I bring down that X. Then I'll get the same thing on the right. And the identity matrix times X is simply X. So that's going to be equal to the inverse of A times B. Okay, so this is very important because it says something. And we're going to figure out what that means in the next slide. Let me just say what the identity matrix is. The identity matrix is equal to, let's say this identity matrix is a 2 by 2. So that's going to look like this. That's identity matrix. It can also be this. So we will deal with a lot of those identity matrices. So let's go ahead and move on. All right, so let's look at this 2 by 2 matrix. We'll just call that A. Okay, so if we take this 2 by 2 matrix, we can find the inverse of that matrix A simply by using this formula. 1 over A times D minus BC times the matrix D minus B, negative B, negative C, A. So what does that mean? Whatever your A term is, you put it under 1 and you multiply by whatever that D term is, subtracted by the B term times the C term. Okay? And then you're going to be multiplying all that by this matrix that's now... What you basically do is you flip the position of D and A in your original A matrix. Okay, you flip them, and then you change the signs of C and B. Okay, notice the difference between those. Okay, so that's pretty simple. You're just going to be using that little formula whenever you're finding the inverse matrix of a 2x2. But what happens when you have a 3x3? Well, let's just say that we have excuse me. You have this matrix A, and it consists of A, B, C, D, E, F, G. I swear I'm not singing. Okay. Okay, so how do we find the inverse of A? Well, you're going to have to be using the concepts of the identity matrices. Okay? Oops. Alright, so how do we use those identity matrices? So these identity matrices can go up to any term that you need to go to, actually. So they can go 4x4, favorite burger at In-N-Out, 5x5, 6x6, and it goes on forever, actually. So it goes from I sub n for any n by n matrix. So to find the inverse matrix, you're going to have to use this idea. So by using elimination of row operation, you're going to change this left side of the matrix. You're going to have to make that into an identity matrix. Okay. So what I mean by that is when you change this A to this identity matrix, you're going to get out this A inverse on the right side. So I think it's easier to just see an example of it, and we'll get to that. But that's the idea. Okay, so I think it's good to get a little practice on these proofs. So we have this small little proof where AC is equal to BC, and the goal is to prove that, or is to prove or show that A is equal to B. And we can do that by asking ourselves, does C inverse exist? If it does, then we can do some math. So basically, we could say that C inverse is equal to B, C inverse. And when you have C times the C inverse, you'll get A times the identity matrix is equal to B times the identity matrix. And A times an identity matrix is just the A, and B times the identity matrix is just B. So in the beginning, we could not simply just divide by C because matrices don't do division. Basically, matrices division is basically the inverse. Okay? And this is done. So let's go back to the inverse formula. Let's say we have this matrix B, which consists of 3, 1, 5, and 2. And we want to find the inverse of B. So since this is a 2 by 2 matrix, we can simply use the formula. And that would be A times D, which is 3 times 2, minus B and C. So if we slow down a little bit, this was our A, this was our D, and in the formula it says that we have to do 1 over A times D minus B. I'm sorry, I should have wrote it the other way. B times C. That's better. So B times C. And if you remember, we have to flip the position of A and D. So now they're going to be 2 and 3. And we have to change the signs of B and C. So this will be -5 and -1. So if we multiply everything out, we get 1 over 6 minus 5 multiplied by this new matrix. And 1 over 6 minus 5 is just 1. So our new matrix for our B inverse is just going to be 2, -1, -5, 3. And that's how you find the inverse for a 2 by 2 matrix. So let's go ahead and do another proof. This proof is a little extensive, but it's good to see. So if you have this matrix, this n by n matrix, we'll call that A. Then A inverse is the inverse matrix of A. So basically these are just statements. And if A times the inverse of A is equal to the inverse of A times A is equal to the identity matrix, A inverse exists. Then A is invertible, which means non-singular, or could also mean non-singular. Otherwise, A is singular, which is not invertible. So we have this theorem, which says that A and B are square matrix invertible. Then A times B is invertible, and A times B, quantity to the inverse power, is equal to B inverse times A inverse. So this is it's a great thing to know when you're doing your proof, which should be coming up right now. So the proof is, since A and B are invertible, then A inverse and B inverse exists to show A times B is invertible, and AB inverse is equal to B inverse times A inverse. Okay, so where do you start? Well, let's pick a nice color. We'll probably go with blue. Sounds like a nice color. Alright, so what we're going to do is Just kidding, we'll go with red. We're going to take this term, and we are going to multiply it to these sides. This left and right side of this B inverse and A inverse. So we should basically prove both of those sides. So in blue, I'm going to show you what we have to do. So basically what we're doing when we're doing this red thing, when we're multiplying it to the left and right, is we're saying this statement. B inverse times A inverse times what gives me the identity matrix. And the second one says what times B inverse times A inverse would give me the identity matrix. And once we figure out what those question marks are, we basically prove both sides that this statement is true. Alrighty. So let's go ahead and get started. So first we're going to take our B inverse times A inverse, and that's something's going to equal to I. Well, you basically try stuff out. Okay, so I'm going to try out AB. So if I place AB there, what will happen is I have A inverse times A, which gives me the identity matrix. And now I have B inverse times the identity matrix times B is equal to I. And you have to state that I times B is equal to B. So now I have B inverse times B, and you should this is good practice. Above the equal sign, you should put question marks because you're not sure yet if it's equal to each other. But then we say that B inverse times B is equal to the identity matrix, and we prove that. Now we need to prove this one, the one on the left. Okay, so we'll take that to the next page, and we'll do it again. B inverse A inverse is equal to identity matrix. Well, let's put AB. Okay, so B times the B inverse, that's going to be the identity matrix. So we'll have A times identity matrix times inverse matrix of A is equal to I. And again, for good practice, we should have the question mark above the equal sign. Okay, then we have to state that A times I is equal to A. And then we can say that A times A inverse is equal to, it could possibly equal to I. But then we know that those two will equal the identity matrix. And then we get that. So then we can say that B inverse times A inverse times this AB is equal to AB B inverse A inverse is equal to I. Then we can say that A B inverse is equal to B inverse times A inverse is equal to AB inverse. And that concludes our proof. So let's move on to an exercise that I find very fun. And basically, we're going to be solving for A. And let me give you the problem because it looks pretty interesting. Boom. So we have the identity matrix plus 2A, and that's the inverse, equals to this matrix negative 1, 2, 4, 5. So we want to know, what does A equal? So basically, we have to use our operations backwards. So that's what's so fun about this. So where do we begin? Well, we're going to begin by saying that I plus 2A, and we're going to apply that inverse to the matrix itself. Alright, so let's deal with the right side. So this is a 2 by 2 matrix, and we're trying to find the inverse. No problem, right? We get to use our formula. That's going to be negative 5 minus 8. Again, it's A times D minus B times C. And then what do we do with the inside of the matrix? Well, we flip positions and we change signs. So the 5 and the 1 are going to change positions. And the 2 and the 4 are just going to change their signs. That's simple enough to remember. Alright, so that's going to give me negative 1 over 13 times the matrix that we have. So now we just have to multiply negative 1/13 to the matrix. Sorry. Alright, so let's go ahead and do that on the next page. That's going to equal negative 5/13, 2/13, 4/13, and 1/13. 1/13, or is it 1/13? Yeah, it's definitely 1/13. Alright, so then we'll have, so let's recall that we had this on the left side, 5/13, 2/13, 4/13, and 1/13. Okay, so what you could do is subtract this identity matrix. Subtract the identity matrix, which is basically, I hope you guys remember, it's just 1, 0, 0, 1. So if we subtract those matrices, we will get negative 18/13, 2/13, 4/13, and negative 6/13. So remember, let's just point that out. It's this term minus this 1, which was basically 13 over 13. And then it was, oh, I'm sorry. I'm thinking ahead of myself. This term is still 1/13. Yep, there we go. And I'm sorry, it's 12/13. Negative 12/13. Okay, There we go. Now we got it. So it's this term minus this 1, and this term minus the 0, this term minus the 0, and then it's this term minus the 13 over 13, which was negative 12 over 13. My mistake. And then we could divide by 2 there, multiply by a half, which is okay. And if you're confused about why we divide by 2 and multiply by a half, when I said that matrices don't do division, well, exactly, they don't do division, and that's why we're not dividing any matrices together. What we're dividing on the left side is a 2, and multiplying basically a k to a matrix, which is totally fine. And then we will get negative 9/13. We'll get 1/13, 2/13, and negative 6/13. Oh, that was a 6. There we go. That is our A. Alright, so next fun one. Let's go with this one. We have A is equal to this matrix 2, 0, 4, 1. Alright, and we have to find A to the minus 3. How do we do that? Well, let's first look for A times A times A. Right? And then we can find an inverse of A cubed. Okay. Let's try that. Okay, so we have to multiply. Good thing this is only a 2 by 2, but still a long process. But whatevs. Alright. If we multiply these two first, let's do this arrow. So we're going to multiply this row with this column. I'm sorry, this column with this row. So it's going to be 2 times 2, which is 4, plus 0 times 4, which is 0. So it's just going to be 4. And if we do the same thing, we're going to get this row times this column, which is 2 times 0 plus 0 times 1, which is just 0. And if we do that with the bottom one, we'll get 8 plus 4, which is 12. Then we get 1. Cool. So those are those two. And then if we do those two together, we'll get 8, 0, 28, and 1. So that's A cubed. And if we were to take the inverse, let's go to the next page. So we had A cubed, which equaled to 8. And actually my sisters make fun of me for making my 8s like that because they call it a snowman, but snowmen are cool, right? So let's take the inverse of this. And then we will get 8 times 1 minus 0 is just 8. And then we have to flip A and D, change the signs for B and C. Negative 28 and 0. I was going to put negative 0. Then we get A minus 3 is equal to 1/8, 0, negative 7 over 2, 1. And that's how you do that. Ta-da. Okay, one more fun one. You have compute P of A when A is equal to 2, 0, 4, 1. Alright, so your P of X is equal to X minus 2. Alright, so P of A, that's going to equal, that's going to equal A minus 2 I sub 2. So that's 2, 0, 4, 1 minus 2 times 1, 0, 0, 1. And your P of A will equal 0, 0, 4, negative 1. And that will conclude this video on linear algebra. So the next linear algebra video will go over elementary matrices and a method to finding a inverse. So I hope you guys found this video informative, and I'll see you on the next video.